Testing, can you hear me? Testing, can you hear me? Testing my voice one more time. Can you hear me? Alright, this video is public now. Alright, this video is public now. So I'm going to be reading the data structures and algorithm book again. And yeah, so last stream I was reading the design chapter. But this stuff, I think I would read a separate book on this. I think this chapter was rushed. Uh, so I'm going to read binary trees this time. Whoops. Trees. Tree structures enable efficient access and efficient update to large collection of data. Okay, first they need to define a tree. Tree is like how they defined it in discrete math, right? When we did the discrete math series. A tree is a finite set of one or more nodes such that there is one designated node R called the root of the tree. If the set T minus R is not empty, these nodes are partitioned into more than n disjoint sets T0, T1 all the way till Tn minus 1, each of which is a tree whose float is R1, R2, Rn, respectively, are children of R. Isn't there a better definition? So we have a graph and we have a tree. So from discrete math, what I remember, graph is just like nodes and edges. So you have a node, a node, n node, and then you have edges connecting those nodes. And you might have a these are vertices. In discrete math, they call these vertices. So might have a one lonely vertex over here, and then maybe this vertex connects to this, I guess, and maybe to this, and then this vertex connect to this, and maybe to this. The important distinction for graphs is that you cannot have two connections. You cannot have two connections, and you can't have self-referencing connections. But you can have one lonely node. Now, a tree is a specific type of graph, which looks more like this. So you have one root node, and then you have the children of the tree. And then those children has childrens. So it's like arranged in a specific order. Here I'm drawing three nodes. Here this node has three childrens. But if every node had two child, then it would be a binary tree. For example, this is a general tree. And then if I had a specific tree with just two nodes, with just two children, then this is a binary tree. So it's not So 3 children is not possible. 1 is possible, 0 is possible, but not 3. Here is a binary tree. At the top is the root node. Binary trees in particular are widely okay. Next. A binary tree is made up of a finite set of elements called nodes. Well, in discrete math, they call it vertices. This set either is empty or consists of a node called the root together with two binary trees called the left and right subtree. Oh, I see. So you have the root, you have these two children, and the two children can make up their own tree. So this tree can be its own tree with this being the root. Similarly, this tree can be its own tree with this being the root. That's the left and right subtree, which are disjoint from each other and from the root. The roots of these subtrees are children of the root. There is an edge from a node to each of its children, and a node is said to be the parent of its children. If n1, n2, nk is a sequence of nodes in a tree such that ni is a parent of ni plus 1 for I from 1 to k, then this sequence is called a path from n1 to nk, such that ni is a parent of ni plus 1. So node 1, node 2 is a parent of node 1, node k is a parent of node k minus 1. Is that what they mean? No, in reverse. Node 1 is a parent of node 2, node 2 is a parent of node 3, node 3 is a parent of node 4. Okay. I think I know what they mean. So if I have this is node 1, this is node 2, this is node 3. So node 2 is a parent of node 1, node 3 is a parent of node 2. So going from node 3 to node 4, it creates a path. However, if I call this node 2, node 2 is not a parent of node 1. So this, and then these two, they don't make a path. The length of the path is k minus 1. Okay, so jumping from one node to another is a path of length 1. Jumping from one node, going up 2 nodes is a length 2. So if you're touching the edges twice, so there are k minus 1 edges in between from node 1 to node 4. One edge, two edge, three edge. So there are 4 minus 1 edges. So the path length is 4 minus 1. If there's a path from node R to node M, then R is the ancestor of M and M is the descendant of R. Thus, all nodes in a tree are descendants of the root of the tree, while the root is the ancestor of all nodes. The depth of the node M in the tree is the length of the path from the root of the tree to M. The depth of the node M. Okay. So the depth of this is 1, 2, 3, 4. So this n1 over here has a depth of 4. The height of a tree is the depth of the deepest node in the tree. Height. So this tree over here has a height of 5. 1, 2, 3, 4, 5. All nodes of depth d are at level d in the tree. So this is level 0, this is level 1, this is level 2, level 3, 4, 5. The root is the only node at level 0 and its depth is 0. A leaf node is any node that has 2 empty children. So this is a leaf node because it has no children. This is a leaf node. This is not a leaf node. An internal node is any node that has at least one non-empty child. Okay. So what? AB. Figure 7.2.1. I don't think they labeled the figures. Illustrates the various terms used to identify parts of a binary tree. Because 7.2.2 illustrates an important point regarding the structure of a binary tree because all binary tree nodes have two children. Wait, hold on. All binary nodes have two children. Sorry, something just came up. All right, going back to the thing. Um, Two restricted forms of binary tree are sufficiently important to warrant special names. Each node in a full binary tree is either an internal node with exactly two non-empty children or a leaf. A complete binary tree has a restricted shape obtained by starting at the root and filling the tree levels from left to right. Each node in a full binary tree is either an internal with exactly two or a leaf. Okay, okay. So you cannot, in a full binary tree, you cannot have one child. It's either two children or no children at all. So if I remove this, so I guess this is an example of a full binary tree. But does it have to be even? I don't know. I mean, never mind. Um, a complete binary tree has a restricted shape obtained by starting at the root and filling the tree by levels from left to right. Oh, I see, I see. So if I make a binary tree, children has to be filled from left to right. So left, right, left, right, and then left, right, left, like that. But what's not allowed is this because I have to start it from the leftmost side. So this here is not a complete binary tree because when I was filling left, right, I should have filled in this first and I shouldn't have gone directly from here. Um, In a complete binary tree of height d, all levels except possibly level d are completely full. Okay, I see. So this one does not have children. It's not full. This level, this depth d is not full because this one does not have children. So in a complete binary tree, I fill it from left to right. All levels are full except possibly the last one. Uh, Fill it and then I stop right here and then it's still a valid complete tree, right? Yeah. Fill from left to right, but only the last level is not full. Also, a full complete tree. Whoops. A full complete tree. Why does it do this? A full complete tree uh, would have two children or no children at all. And it's also filled from left to right. Figure 7.2.3 illustrates the difference between a full and complete binary tree. Mean a tree can be full and complete at the same time. There is no particular relationship between these two tree shapes. That is, the tree of figure 7.2.3 is full but not complete. So this is full, but it is not complete because this part is not filled in. While B is complete but not full. Complete. Oh, it's not full because this one has one child. The heap data structure is an example of a complete binary tree. The Huffman coding tree is an example of a full binary tree. While these definitions for full and complete binary tree are the ones the most commonly used, they are not universal because the common meaning of the words full and complete are quite similar. Uh, every binary tree is either complete or full. That's not true. no binary tree. It's none of the above, right? Suppose T is a binary tree with 14 nodes. What is the minimum possible height of T? So 1 node, 2 node, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12, 13, 14. So the height is 1, 2, 3. The height is 3. Well, the minimum possible height is 3. And this is the same question. The depth of this tree, I mean, for which node? 1, 2, 3. They do not have depth. Wait. Depth is for the node, right? The depth of the node. Okay. The height of the tree is the depth of the deepest node. Yeah, trees have height, not depth. How many nodes in the tree have at least one sibling? So 1, 2, 3, 4, 5, 6. 6, right? They're on the same depth. Sibling means they're on the same depth and have the same parent. What is have the same immediate parent? What is the depth of this tree? This is the same question. A recursive data structure is a data structure that is partially composed of smaller and simpler instances of the same data structure. For example, linked lists and binary trees can be viewed as recursive data structures. A list is a recursive data structure because a list can be defined as either an empty list or a node followed by a list. Binary tree is typically defined as an empty list or a node pointing to two binary trees, one its left child and the other one its right child. Okay. So wait. Here in C, I will try to make a tree. Struct binary tree. Is it common convention to uh, common convention that the struct name starts with a capital letter? So binary tree, its node is no. Binary tree. Binary tree. Binary tree node. So the node value. So the node value is so the node has a value. Let's say it's integer. So this binary tree will store integers, and it has a left subtree and a right subtree. Left subtree, which will be a pointer. Up, struct pointer, struct, and a right subtree. So the node value and the left subtree and then the right subtree goes to the other nodes. Yeah. Suppose you want to compute the sum of the values stored in a binary tree. So 20 plus 5, 10. The full binary tree theorem. Okay, let's think about I'm going to do this. Struct binary tree node. Where's the help? um my tree I will have fill value. Void fill values. Tree. And then I will put my tree here. I have to pass a pointer, right? Pointer. Yeah. Fill values. Fill values. Um so tree dot value is 20. 25, 10. 25, 10. And then I will make another tree. Okay, so I will make a complete tree. This is what I'm going to do. Um, um, huh. Then I will make a new tree. And then I don't know what to do. Let's try int values 25, 10. Hold on. 25, 10, 15, 30, 40. Oops. 25, 10, 15, 30, 40. Let me think about this. Initialize and get tree. For int I less than 1, 2, 3, 4, 5, 6. I plus plus. This first I initialize the root. And then current tree is the root. First I initialize the root, then the current tree is the root. Malloc size of struct binary malloc, binary root tree, root current tree. No, maybe I'm getting this wrong. So first fill 20, then in the children of the root tree fill the left and right subtree. Yeah, I think I'm getting this wrong. Wait. So initially what I was thinking is to malloc it because I'm going to have a reference of it saved in the left and right subtree, right? Maybe I fill the root. If I want to fill another value down, I go the left side. Okay, this is the first time coding about trees. So I fill the root first. Fill the root first. Root value 20. And then void add to tree. Add a value to the tree. If I want to add a value to the tree, int val, I go the leftmost side. I go the leftmost side. So I initialize the root and initialize the root. Root left subtree is null. Same for the right. Right subtree is null. Okay, I think I understand. So both left and right are initially null. And I fill the root in. Initialize and get tree. Int val. Then I should put val in here. Then how I will initialize it is this array is just temporary. I'm going to delete it. So how I'm going to initialize it is I will start with this my tree and then I will add to my tree. Add to tree, add to tree, add this value to tree, add to tree. The next value is 5. So add 5 to tree. So what it's going to do is that what it will do is that it will go to the left subtree. If left subtree. But I want it to be a complete binary tree, right? So filling from left to right. Oh, this is going to be difficult. So do I have to separately save the height of the tree? Let me think about this. Left subtree, it will check if it's null, if Somewhere there has to it has to save the height, right? Should I save the height as well? Height. Height is saved. Height is saved. Actually, no. No. It should be. It should be next fill. The root tree will save the next fill. Maybe. Or should it save the height? Should I save the next fill? The next fill is like next time I want to add a value, where do I add the value? That's the next fill. But thing is I will have to save the height, right? How will I know if I'm adding to a tree and it's like partially filled? How will I know if it's like depth of 4? Would I have to check every left right subtree? Like, because at the start I wouldn't know the height. So would I have to check the height first? Let's just save the height value maybe. Height value. And the initialize and get root. Root. So height from the root. Root height is 0. And should there be a reference going back to the parent? Or maybe not, forget it. So the height is 0. So what it's going to do is starting from the root of the tree, keep going height down at every from left to right. So the left subtree. If the left subtree is null, I'll fill this up later. If the left tree is null, then you have a new tree. With the value inside. Then you have a new tree and the tree dot left tree. Left subtree is this new tree. Actually, no. Assume that the height is 0. If the height is 0, if the height is 0, we create a new tree, add it to the left subtree. Then the height is 1. If the height is 0, if the height is 0, if the height is 0, let me think about this. I'm thinking recursive. We have to do this recursively. Maybe check each node down. Okay, let me tell you what's going in my head. So we have the root already saved up. It's a complete tree. Now if I want to add a new value, Start from here. Check this, check this, check this. This is filled, but the height is 1, 2, 3. The height is 3, right? We need to check if all the depth is filled. So we have to go back, right? Go back and then go back. And then go back to the root and then check this side. And this depth was such thingy is confusing because I don't know when was the last time I quoted this. Okay, let me think about this. So first when it starts with a height of 0, it just fills up this and then it fills up this, right? So first what it's doing is 5, 5 and 10. So first what it's doing is filling up 5, filling up 10, but that's just easy. But now if the height is increased, maybe I should return an int if it added a new value. Return int and assume it returns 0. Okay, let's see. Or maybe not. Maybe I shouldn't have the height. I should have the next fill value I was talking about. Next fill is root left subtree. And then if you want to add the tree, we add it to the next fill. This is the root. We add it to root next fill. Root next fill. Next fill maybe. Hold on, I feel like I'm doing this wrong. Let me see what they did. Full binary tree theorem. Some binary tree implementations store data only at the leaf nodes using the internal nodes to provide structure to the tree. By definition, a lead node does not need to store pointers to its empty children. More generally, binary tree implementations might require some small amount of space for internal nodes and a definite amount of leaf nodes. Thus, to complete the space required by such implementations, it is useful to know the minimum and maximum fraction of each node of the nodes that are leaves in the tree containing n internal leaves. Fortunately, this fraction is not fixed. A binary tree n has of n internal nodes might have only one leaf. This occurs when internal nodes are arranged in a chain ending in a single leaf as shown in figure 7.4.1. this example, the number of leaves is low because each internal node has only one non-empty child. To find an upper bound on the number of leaves for a tree of n internal nodes, first note that the upper bound will occur when each internal node has two non-empty children. That is, when the tree is full. However, this observation does not tell what the shape of the tree will yield the highest percentage of non-empty leaves. Turns out not to matter because all full binary trees with n internal nodes have the same number of leaves. This fact allows us to compute the space requirement for a full binary tree implementation whose leaves require a different amount of space from its internal nodes. Full binary tree theorem, the number of leaves in a non-empty full binary tree is one more than the number of internal nodes. Okay, we can use induction for this. This is what I'm assuming they do. So you start with one node. This root is a leaf, right? And then it's a full tree, so it will have two children. So now, because it's two children, the leaves is one more than the internal node. You add two children. Leaf, leaf, leaf. Three leaf, two internal node. Three internal node, four leaves. So I see what happens here. So every time you add two children, the previous leaf becomes an internal node, so the number of internal nodes increase by one. But because you added two children, the number of leaves increases by two. Wait, yeah, the number of leaves also increases by one. Yeah, because when you add children to this node over here, the number of leaves will decrease by one because this leaf now has children. But at the same time, because of these two children, then it increased by two. Minus one leaf plus two leaves, and then plus one internal node. So overall plus one internal node plus one leaf. So the number of so the difference between the internal node and leaf stays the same. Proof is by mathematical induction on n the number of internal nodes. What is the other theorem? The number of empty subtrees in a non-empty binary tree is one more than the number of nodes in the tree. The number of empty subtrees. So the children of the leaves is null. Children of this leaf is null. So the number of subtrees is 2 times the number of leaves. So the number of leaves is number of leaves 1, 2, 3, 4, 5, 1, 2, 3, 4. Number of leaves is plus 1 gives the number of internal nodes. Leaves, sorry, I got it the other way around. Number of internal nodes plus 1 gives number of leaves. Then each leaf has 2 empty subtrees. So twice the number of leaves is the number of empty subtrees. Let's call it empty subtrees. Empty subtrees, internal nodes. So the total number of nodes is the leaves plus the internal node. Leaves plus the internal node. And then the internal node is leaves minus 1. Leaves minus 1. So the number of nodes is 2 leaves minus 1. The number of nodes is number of empty subtrees minus 1. Number of empty subtrees is one more than the number of nodes in the tree. That is correct. Number of nodes, one more of that gives empty subtrees from here. Okay. Binary tree traversal. Often we wish to process a binary tree by visiting each of its nodes, each time performing a specific action such as printing the contents of the node. Okay. Any process for visiting all of the nodes in some order is called a traversal. Any traversal that lists every node in the tree exactly once is called an enumeration of the tree's nodes. Some applications do not require that the nodes be visited in any particular order, so as long as each node is visited precisely once. Okay, I will read this chapter and maybe I might end my stream because something just came up. I might end the stream earlier than expected. So, just a heads up. For example, we might wish to make sure that we visit any given node before we visit its children. This is called a pre-order traversal. A, B, D, we have C, E, G, F. Pre-order traversal, we make sure that we visit any given node before we visit its children. So A, we visit A first, and then we visit the children of A. So B, and then we visit C. If are we going depth first, or are we going breadth first or depth first? Pre-order enumeration for a tree of figure 7.5.1 is A B D A B D C E G F H I. Alternatively, we might wish to visit each node only after we visit its children and their subtrees. For example, this would be necessary if we wish to return all nodes in a tree to free store. We would like to delete the children of a node before deleting the node itself, but to do that requires that the children's children be deleted first, and so on. This is called a post-order traversal. So starting from D, so we go down, start from D, B, A, then go down, print G, print E, print C, and then go down, print H, print F, and then go down. Sorry, wait, no, I got this wrong. We go down, print D, print A, before printing, sorry, print D, print B, before printing A, visit the children of C, before printing C, visit the children of C, before printing E, visit the children of E. Now print G, print E, before printing C, print the children of C. Before printing F, print the children of F. So H, I, then F, C, and then finally A. Yeah. Most order. Oh, there is a lot of recursion here. D, B, and then don't print A yet. Go to the children of A. Go to the children of E, print G. I get the main point. The in order traversal first visits the left child and then visits the node and finally visits the right child. The binary search tree makes use of this traversal to print all nodes in ascending order of value. In order, first visits the left child, then visits the node, finally visits the right child. So B, D, A, G, E, C, H, F, I. So it's printing the leftmost first. There is no left here, so then it will go right. What's the difference between BDA, BDG, BDA? Oh, I see. So left first, then the parent, then the right. Okay, I see. So DBA, then C GEC and then HFI. Okay, I understand. Okay, implementation, I want to do that myself. I don't want to look at the thing, but I do want to check the what the thing is, what the interface is. So they have a value, set value, left, right, and is leaf. I just want to add to the tree. That's the main part. Okay, I will hold on. Let me see if I am free. How long is the next chapter? I really wanted to complete the thing. When you print out the nodes of a binary tree, the leaf nodes appear in the same relative order for pre-order, in-order, and post-order traversal. So pre-order, in-order, post-order. So in order, you do left, parent, right, left, parent, right. Post-order, after we visit the child. So left, uh, right, parent, D, B, C, E, H, is G, E, H, I, F, C, A. Yeah, left, right, parent is post order. And then pre order is A, B, D. So parent and then left and then right. A, B, D. A already visits C, E, G, F, H, I. So the left comes first and right comes later, right? In all of these transitions. So pre-order is parent left right. Post order is left right parent. Uh, CE left right parent. And then in order is left parent right. So the left and right are in the same order, right? Yeah. If you're given the order of the nodes as visited by pre-order traversal and the order of the nodes as visited by an in-order traversal, do you have enough information to reconstruct the original tree? Assume that the nodes all have unique values. You're given the order of the nodes as visited by pre-order traversal and the order of a node as visited by an in-order traversal. In order left, parent right, pre-order. Pre-order is pre-order is parent, then left, then right. Yeah, I think we can, like, intuitively. Oh, no. Oh, whoops. Yeah, it's the same question. Or is it? Pre-order and post-order? I think, yeah. Nope. I want to see. Pre-order traversal prints ABC and the post-order traversal prints CBA. Can you determine the original tree from this information? Pre-order is left, right, parent, right? Left, right, parent. Post-order is left, right, parent. And pre-order is parent, left, right. Parent, left, right. Pre-order. Pre-order is parent, left, right. Then post or pre-order. Parent, actually. Parent, left, right. Post order is left, right, parent. Left, right, parent, CBA. Traversal prints left, right, parent. I just keep coming back to it. Left, right, parent, CBA, post order print CBA, and the pre order parent left, right, pre order parent left, right. Okay. So pre order parent left, right is A, B, C, and then the post order is CBA. CBA post order is left, right, then parent. So A, B, C, and then the post order is CBA. This is empty, empty, empty. Empty, empty. But if I have empty, why does it print this? B, C. Post order. So if the tree is on the right, then we can't determine with this information, we can't determine whether it's this tree or this tree. Okay, I understand. All right, I will end the stream here then. And yeah, I'll see you guys next time. Bye.